Welcome to The Explainer. Today, we're diving into a high-level executive technical briefing, and I'm going to be putting on my hat as a senior technical strategic consultant. We are going to strictly deconstruct the monumental propulsion strategy shifts that just emerged from the 2026 SAE WCX. Now, for those of you actually engineering the future of mobility, you already know the stakes are incredibly high right now. We're navigating a highly volatile environment, and the legacy strategies that got us here just aren't going to get us to 2030. So we're going to apply a rigorous McKinsey-style top-down approach to really make sense of this data.
For years, the entire global mobility industry basically operated under one very specific baseline assumption, that a rapid, monolithic transition to pure battery electric vehicles was absolutely inevitable. But the engineering and regulatory realities presented at WCX 2026? They've completely, drastically shifted that narrative. The internal combustion engine isn't dying off quietly. Actually, it is actively being fundamentally re-engineered.
Okay, let's look at this number, because it's a big one, greater than 50%. This represents a massive breakthrough in indicated thermal efficiency coming out of research at Tongji University. This definitively proves the internal combustion engine is undergoing a profound thermodynamic renaissance. Hitting 50% was, once considered an absolute physical pipe dream for light-duty gasoline engines. But today, it's a verified laboratory reality, and it completely rewrites the calculus for global platform architectures.
To structure our analysis today, we're keeping things mutually exclusive and collectively exhaustive. We'll cover 1. The propulsion strategy dichotomy. 2. Regulatory shifts and compliance. 3. HEV and EREV strategic pillars. And 4. The ICE thermodynamic renaissance. Let's get right into it. Starting off with Section 1, the propulsion strategy dichotomy, moving from monolithic BEV to multi-pathway resilience. We first have to establish the macro-strategic situation and the intense supply chain complications that are really driving this entire industry-wide pivot. Because, let's be honest, you cannot engineer a vehicle in a vacuum. You're engineering it within the very real constraints of global supply chains. Severe geopolitical vulnerabilities, specifically China's near monopoly on critical battery metals and refining capacities, have literally forced OEMs into a tactical retreat from aggressive pure electric mandates. The capital risk is just way too high, so Western OEMs are now heavily prioritizing architectural sovereignty. A multi-pathway ecosystem isn't just a nice-to-have anymore, it's a vital corporate defense mechanism.
Moving to Section 2, Regulatory Shifts and Compliance, the technology-neutral paradigm.
So, the supply chain complications we just talked about are perfectly mirrored by some pretty significant regulatory relaxations. Regulators are looking at the exact same lagging infrastructure and EV adoption data that you and I are. And the policy landscape is finally providing a strategic buffer. For instance, the U.S. EPA is anticipated to delay light-duty Tier 4 standards, basically maintaining 2026 levels through the 2027 or even 2028 model years. NHTSA is resetting CAFE standards, and over in Europe, the EU Commission actually moved the review of their 2035 ICE ban forward to 2025. This introduces massive compliance flexibility, giving OEMs the green light to aggressively fund high-efficiency hybrids and internal combustion programs. This is a totally critical statement from Peter Simhauser, NHTSA's chief counsel, and it perfectly validates what we're calling a technology-neutral regulatory shift. CAFE standards are fundamentally meant to regulate the efficiency of internal combustion vehicles, not to act as some backdoor mandate for fleet-wide electrification. This entirely changes the engineering trajectory, giving traditional OEMs the breathing room to allocate R&D back into thermodynamics.
Which brings us to Section 3, HEV and EREV strategic pillars, bridging gaps and securing supply chains. To actually resolve these market and regulatory complications, we divide the engineering response into 2 core pillars. We really have to contrast 2 distinct OEM philosophies when it comes to hybrids. On one hand, you have the transitional bridge paradigm. This treats hybrids as a way to just buy time, letting pure BEV tech mature and waiting for grid infrastructure to catch up. This is mostly for urban mobility and passenger cars. But on the other hand, we have the permanent destination paradigm. This is the hard realization that for heavy towing, long-haul transport, and non-road applications, liquid fuels just have an unbeatable physical energy density. In these use cases, hybrids aren't a bridge at all. They are the permanent, optimal engineering solution. Strategically, these hybrid architectures are acting as a literal firewall. By utilizing drastically smaller battery capacities, OEMs structurally desensitize their bill of materials from those monopolized refining markets we mentioned earlier. It drastically cuts dependency on rare earth metals, bypasses regional grid infrastructure deficits, and, crucially for the folks in the C-suite, it maintains positive cash flow while still achieving really substantial life cycle emissions reductions.
On to Section 4, the ICE Thermodynamic Renaissance, pushing the limits of physics.
Now, if hybrids are here to stay as a strategic pillar, the internal combustion engine acting as the generator inside them has to be pushed to the absolute limits of physical efficiency. And here is exactly how they are doing it. Engineers are combining an active pre-chamber to shoot plasma jets into an ultra-lean air-fuel mixture. We're talking about running at a lambda of 2.0 with an aggressively boosted Miller cycle. By doing this, they are breaking through previous physical limits of heat loss. They're getting stable combustion where previously you'd literally just get misfires, dramatically boosting thermal efficiency and virtually eliminating engine-out NOx emissions. It's brilliant.
And the WCX data shows just how diverse this thermodynamic renaissance really is. These aren't one-size-fits-all solutions. They are deeply tailored to specific platforms. We're seeing everything from ultra-lean 2-liter passenger car concepts all the way up to massive machine learning-optimized open bowls for heavy-duty diesels. The engineering toolbox has literally never been this vast.
Tracking these thermodynamic performance metrics is fascinating. We see Tongji University's 2-liter ultra-lean breakthrough yielding over 50% efficiency. There's a hydrogen Carnot opposed piston engine hitting a staggering 58.7% thermal efficiency. But I really want to zoom in on this 11.6-liter heavy-duty gasoline concept from IAAV because the commercial implications of this specific architecture are absolutely massive. So to meet upcoming EPA 2027 regulations, Class 8 heavy-duty diesel engines are going to require incredibly complex, bulky, and wildly expensive after-treatment systems. Think dual-dosing SCRs and massive diesel particulate filters. It's a total capital trap for OEMs. But AAV bypassed this entirely. By adopting a sky-high 16.3-to-1 geometric compression ratio combined with stoichiometric exhaust gas recirculation, they engineered a heavy-duty engine that actually runs on gasoline. Because it runs at stoichiometry, it can use a simple, cheap, tightly coupled three-way catalyst to control emissions. It completely sidesteps the massive capital costs of diesel aftertreatment.
From a total cost of ownership perspective, this is a total game changer. This shift to heavy-duty gasoline saves commercial fleet operators an estimated $86,600 over a 750,000-mile service cycle. It's an incredible example of how rethinking fundamental thermodynamic architecture directly solves complex regulatory and financial constraints.
Finally, Section 5, Strategic Imperatives for 2026, Engineering for a Volatile Landscape.
Let's distill the bottom line up front for your own vehicle programs. Success in this volatile era will not belong to the companies who stubbornly stick to a single technological path. It's going to belong to the systems architects who pivot to multi-pathway ecosystems. You absolutely must deploy radical platform modularity, chassis that can seamlessly accept BEV, EREV, or advanced ICE propulsion. You need to master digital twin simulation because managing the thermals and power flow of these multi-energy platforms is incredibly complex. And above all, you have to actively design out geopolitical supply chain vulnerabilities at the elemental level, right there during the initial CAD phase. Which leaves us with this final strategic imperative to think about. As the internal combustion engine fiercely reclaims its role within a multi-pathway propulsion ecosystem, how will your specific R&D portfolios adapt to secure both strict regulatory compliance and ultimate supply chain resilience? Honestly, it is the defining engineering challenge of the decade. Thanks for joining this explainer, and we'll see you next time as we continue to break down the science shaping our world.
Hey everyone, and welcome to The Explainer. So, as a technical strategy consultant looking at the whole automotive landscape right now, I've spent some serious time distilling the absolute avalanche of data that just came out of the 2026 SAE WCX in Detroit. And look, we are staring down a fundamental paradigm shift here. Historically, right, we've treated the battery energy storage system, the BESS, as basically a passive chemical reservoir. Just a dumb bucket of energy, essentially. But the clear engineering consensus from Detroit proves that the BESS has definitively transitioned. It is now an intelligent, software-defined node within a much broader energy ecosystem. So today, we're taking a top-down approach to completely deconstruct this transformation for you engineering leaders.
To make sense of this overwhelming amount of technical data, we're applying a strict MISI framework. We're structuring the evolution of BESS into 4 mutually exclusive, collectively exhaustive pillars: intelligent BMS, solid-state batteries, sodium-ion scaling, and thermal runaway multi-scale modeling. Let's dive right in.
All right, starting off with Pillar 1, intelligent BMS, specifically looking at ML and AI diagnostics.
Now, This is exactly where advanced software intelligence converges with high-fidelity electrochemical sensing. We are now actively probing the chemistry in real time, all thanks to the commercialization of electrochemical impedance spectroscopy, or EIS. Traditionally, EIS was strictly a lab technique. It was just way too complex and expensive. You apply a periodic current stimulus across multiple frequencies, measure the voltage response, and then analyze it all through fast Fourier transform algorithms to calculate internal impedance. But what's absolutely crazy here is that we're moving this laboratory-grade diagnostic directly into next-gen commercial automotive packs. We're talking about detecting deep physical phenomena, like electrode cracking or the very onset of lithium plating, way before they ever become catastrophic. And this leap, it fundamentally changes our entire approach. Think about a conventional BMS. It's incredibly reactive. It relies on standard lookup tables, uses module-level sensing, and samples data at, maybe 100 milliseconds to a full second. In stark contrast, an intelligent EIS-ready BMS is predictive. It incorporates actual machine learning. We're talking long short-term memory and gated recurrent unit networks tracking actual voltage deviation trajectories. We're looking at cell individual sensing with sampling rates dropping from 10 milliseconds down to sub-1 millisecond on-chip FFT calculations. We aren't just reacting to faults anymore, guys. We are literally forecasting degradation trajectories long before a safety incident even has the chance to happen. Moving right along to Pillar 2, solid-state batteries, representing the absolute bleeding edge of high-performance chemistry. The industry essentially has a dual mandate right now: completely eliminate those flammable liquid electrolytes for intrinsic safety, while exponentially boosting our energy density, 375 watt-hours per kilogram. Just let that number sink in for a second. It's massive. Stellantis and Factorial Energy recently validated large-format, automotive-sized solid-state cells hitting that exact energy density using their FEST tech, Factorial Electrolyte System technology. To put that into perspective for a second, traditional NMC lithium-ion cells hit a hard physical wall right around 250 to 280 watt-hours per kilogram. Shattering that limit means OEMs can completely shrink the physical footprint and weight of the pack, or, dramatically extend the range within that exact same packaging space. And the charging capabilities? Completely shifting. Amcera demonstrated an absolute benchmark at the Congress. By leveraging their proprietary sulfide solid-state electrolytes, they fast-charged from 0 to 80% state of charge in under 15 minutes. And they're pulling this off at a charge rate exceeding 4C. That kind of high discharge, high charge capability means vehicles can finally deliver powerful, instantaneous acceleration without instantly triggering that annoying thermal throttling we see in traditional lithium-ion packs. But look, we have to remain grounded in commercial reality here. The roadmap from WCX shows a very phased approach. Between 2026 and 2028, we're really just going to see hybrid or gel solid-state systems acting as a bridge. True automotive solid-state won't hit scale until that 2028 to 2032 window, and true mass market penetration slated for post-2032. The reality is, overcoming the solid-solid interface resistance, basically maintaining that physical contact between the electrode and electrolyte when the volume changes without needing massive pack-level compression, that remains the primary engineering hurdle we have to solve. All right, this brings us to Pillar 3, sodium-ion scaling, our crucial infrastructure alternative. Think about it this way. If solid-state is our answer for high performance and premium range, sodium-ion is the absolute strategic necessity for volume, infrastructure, and, honestly, geopolitical resilience. Looking at these strategic trade-offs, Western OEMs are acutely aware of the massive supply chain vulnerabilities tied to lithium, cobalt, and nickel. Now, sure, sodium-ion chemistry sits lower on the energy density curve, around 140 to 160 watt-hours per kilogram, which is obviously its major challenge. But sodium is globally abundant, and it is incredibly cheap. That makes it a structurally perfect fit for entry-level EVs and heavy commercial vehicles, where weight isn't quite as critical, but cost and supply chain security are absolutely paramount. And it's not just about the vehicles. Beyond the car itself, sodium-ion is poised to totally dominate utility-scale stationary grid storage. Its highly stable chemistry means you can rapidly deploy it with a vastly simplified thermal architecture. Listen, as we roll out these megawatt charging systems for commercial fleets, which pull these insane 3,000 amp spikes, local grids literally cannot cope. Sodium-ion provides a highly dependable, localized stationary BSS buffer to stabilize that massive grid load. Finally, we move to Pillar 4. Thermal runaway multi-scale modeling. Because regardless of the chemistry, whether we're pushing NMC, rolling out sodium-ion, or piloting solid-state,
Managing the thermodynamics and the physical safety protocols is always our most critical engineering directive. The UL Research Institutes presented this highly sophisticated 3-step multi-scale approach to crack this problem. Step 1 is modeling down at the microscopic level, understanding the exact kinetics of the exothermic reactions and the electrolyte interactions. Step 2 scales that up to the cell level, focusing heavily on venting and gas emission characterization. And this is especially vital for the new sodium-ion architectures, right? Engineers need to precisely map out the toxicity and flammability profiles of those specific vented gases. Finally, step 3 is pack-level modeling, where some fascinating recent findings actually show that radiative thermal transfer plays a way larger role in thermal runaway propagation in modern lightweight packs than our old conduction models ever suggested.
But here's the really big question. How do we actually compute all this intense heat data in real time on a moving vehicle? Well, this brings us to a massive breakthrough presented by Trina Storage. Traditionally, computational fluid dynamics, or CFD, gives us the highest accuracy for thermal modeling, but it takes literal days to compute. It is mathematically impossible to run that on an edge BMS. To speed things up, engineers usually use lineal time invariant reduced order models, LTI-ROMs. The fatal flaw there? LTI models completely break down and lose their accuracy the second your coolant flow rates vary, and in real-world driving, they vary constantly. Trina's breakthrough structurally decoupled the entire system. They modeled the solid components using traditional LTI, but they completely separated out the fluid channels, modeling those dynamically using Newton's cooling law. Then they just couple them together at the fluid-solid interface. The result is wild. We can now achieve CFD-level fidelity that executes in mere seconds, which means engineers can finally embed these high-fidelity predictive algorithms directly into real-time vehicle-bound edge controllers, a real game-changer.
All right, let's pull this all together. Our final focus, strategic future engineering integration.
When you step back and put all these pieces together, we are staring down a unified strategic engineering directive for the coming decade. We are officially moving out of the era of isolated, siloed mechanical engineering and stepping fully into cross-disciplinary integration. As this quote from the SAE expert consensus perfectly lays out, you just can't design a battery pack in a silo anymore. Modern best engineering demands true co-design. We are seamlessly merging electrochemistry with AI, advanced power electronics like silicon carbide, and a highly complex multi-scale thermodynamics. You literally cannot optimize the cell today without simultaneously optimizing the edge AI that's going to govern its liquid cooling channels in real time.
So I want to leave you with this final thought to chew on. Physical prototyping has simply become way too expensive and way too slow to keep pace with this level of systemic complexity. The future undoubtedly belongs to the engineering teams who master the digital twin. As BSES fundamentally shifts from being just isolated chemical silos to active AI-driven grid nodes, is your engineering workflow structurally prepared for this massive paradigm shift? Thanks so much for joining me in this explainer. Keep innovating out there, and I'll catch you next time.
All right, let's dive right into this executive explainer. I'm your host, and today we're putting on our senior technical strategy consultant hats. We are executing a top-down, rigorous deconstruction of the SAE WCX 2026. If you're an automotive systems engineer or a platform architect, you already know the unbridled optimism of early electrification is completely shifted. We aren't operating under idealistic mandates anymore. We've entered a highly pragmatic, physics-driven paradigm that we're calling resilient propulsion.
To cut through the industry noise, we're going to use a strict MECE framework, mutually exclusive, collectively exhaustive, to break this transition down into 4 distinct pillars: 800-volt systems, wide-bandgap semiconductors, magnet-free motors, and intermodal e-solutions.
Section 1. The Resilient Propulsion Paradigm. So, look, OEM architectures aren't just fighting tailpipe emissions anymore. What we're actually fighting now are brutal physical thermal limits and highly concentrated fragile supply chains. Survival in this new mobility landscape demands extreme platform modularity. OEMs absolutely have to hedge against raw material volatility without getting crushed by redesigned CapEx. Think about Stellantis' STLA large platform, for example. It's natively engineered to handle massive 400-volt and 800-volt BEV architectures, right? But it still perfectly retains the physical layout flexibility to run advanced ICE and hybrid propulsions down the exact same assembly line. That is what architectural resiliency looks like in action.
Moving on to Pillar 1, the 800-volt architecture shift.
This voltage shift isn't just a trend, it's a fundamental necessity to bypass legacy bottlenecks. And the core of the problem here is inescapable physics, specifically Joule's first law. Heat generation in a conductor is directly proportional to the square of the electrical current. So if the market is demanding sub-10-minute fast charging, and they are, and you try to push that at 400 volts, you have to exponentially crank up the current. That creates an impossible thermal load, meaning you need massive heavy copper wiring and crazy complex liquid cooling systems just to keep the cables from literally melting. But the elegant solution is just simple math. By jumping your architecture from 400 up to 800 volts, you double your power delivery while keeping the current mathematically constant. It's a total game changer. This fundamentally removes those physical thermal choke points on DC fast charging speeds. Plus, it completely optimizes your unsprung mass because you can use much thinner, lighter wiring harnesses.
Which brings us to Pillar 2, wide-bandgap semiconductor dominance. Now, to actually handle that 800-volt shift, we need a complete materials science revolution at the power electronics level. Based on the WCX data, traditional silicon IGBTs are being entirely marginalized. They're simply way too lossy at high frequencies. Instead, silicon carbide and gallium nitride are aggressively taking over the high-voltage traction and onboard charging applications.
The real magic here is the solid-state physics. Just look at the bandgap energy. Jumping from silicon's 1.1 electron volts up to silicon carbide's 3.3 EV lets us hit drastically higher switching frequencies without massive leakage. And what does that mean for your powertrain in the real world? It means an inverter efficiency jump from around 97% to over 98.5%. Now, you and I both know in the world of power electronics, a 1.5% gain is absolutely massive. But here's the strategic so what? 45%. Silicon carbide's superior thermal conductivity actually cuts total heat generation by 66%. If you're a thermal engineer, that is music to your ears, because it allows you to slash your heat sink volume by 45%. You are fundamentally altering the vehicle's packaging density, enabling true single-unit drive modules where the electronics are integrated directly onto the motor.
All right, Pillar 3, magnet-free and axial flux motors. Let's look at the electromechanical heart of the system. We absolutely have to talk about the geopolitical risks tied to rare earth mining, specifically neodymium and dysprosium. To hedge against this supply chain vulnerability, the industry has basically fractured into 4 mutually exclusive research clusters. First, IPMSM optimization, where they're aggressively shrinking the magnets using flux weakening. Second, ferrite-assisted synchronous reluctance motors, ditching rare earths entirely for cheap ferrite. Third, axial flux and PM vernier motors for that extreme packaging density. And fourth, the ultimate defense, completely magnet-free wound-field synchronous motors, or WFSMs. We're even seeing institutions like Nanjing University use 2-stage brushless, contactless excitation to power the rotor magnetically, completely eliminating the mechanical wear of traditional carbon brushes.
But wait, this introduces a massive engineering hurdle. If you swap rare earth magnets for highly conductive copper windings directly on the rotor, you generate immense resistive waste heat, those I²R losses right inside the spinning rotor. So it begs the million-dollar question, how on earth do we prevent catastrophic thermal degradation in these magnet-free topologies?
Well, the engineering consensus, backed by research from NREL and Oak Ridge National Lab, is that high-torque commercial applications are going to need a really aggressive twin-fluid cooling strategy. You're literally injecting dielectric oil straight into the internal machine to cool the spinning rotor, while simultaneously running a traditional water glycol coolant jacket around the outer stator. Yes, it adds significant mechanical complexity and some really tough sealing requirements, but it secures that vital independence from fragile global magnet supply chains. Moving to Pillar 4, E-axle and E-trailer solutions.
Scaling this integrated tech outward means looking beyond just passenger vehicles to intermodal commercial applications, where OpEx optimization is literally everything. And this is where we see a radical commercial innovation taking off, the E-trailer. We are talking about heavy-duty trailers fitted with their own 800-volt E-axles and massive internal battery packs. So, instead of just dragging dead weight, these trailers are actively pushing the towing vehicle. They use embedded real-time control to perfectly sync up with the prime mover.
The impact here is staggering. By actively assisting the prime mover, these distributed e-trailer control systems can drive down overall fleet CO2 emissions by up to 40%. 40%! And when you pair that with megawatt charging systems, so you can juice up these massive packs during legally mandated driver rest periods, you completely validate immediate, scalable commercial viability.
Final synthesis, system integration, and the software-defined future.
Because remember, none of these 4 pillars function in a vacuum. The solid-state battery, the wide-bandgap inverter, the magnet-free motor, the e-trailer, they are all governed by centralized compute platforms mastering digital twin simulations of thermal loops and smart chassis dynamics. So, as we wrap up this explainer, I want to leave you with one final provocative thought. The days of just bolting an electric motor to a legacy chassis, that era is over. The critical question for every mobility systems architect and engineering director watching this is, does your platform strategy rely on vulnerable legacy nodes, or have you engineered true architectural sovereignty? Mastering these interdependent physics and supply chain realities isn't just about efficiency anymore, it's quite literally about the survival of your platform. Thanks for joining me for this explainer. Keep engineering for the future, and I'll see you next time. Welcome to this strategic explainer. I'm stepping into my role as a senior technical strategy consultant today to give you a highly technical, top-down briefing tailored specifically for you, the automotive engineer. We're going to dissect the massive infrastructure paradigm shift presented at the SAE WCX 2026 Congress in Detroit. Because if you're designing the vehicles of tomorrow, you simply cannot afford to ignore the roads they drive on anymore. We are moving rapidly from a world of isolated vehicle dynamics to one of total ecosystem integration. To really grasp this shift, we've got to fundamentally reframe our mental models. The era of isolated, siloed vehicle development, it's completely dead. The industry is hurtling toward connected, cooperative, and automated mobility, or CCAM. And in this new reality, the road itself transforms from a passive physical substrate into an active, intelligent participant in your vehicle's operational domain. For engineering teams, this means your vehicle's performance, safety, and efficiency are now inextricably linked to the digital and physical health of the infrastructure it drives on.
Utilizing a top-down MEC framework, meaning our analysis is mutually exclusive and collectively exhaustive, we're going to systematically dissect this cyber-physical system across 4 distinct pillars: proactive roadway maintenance, intelligent V2X service nodes, bidirectional charging, and low-carbon construction materials. All right, let's dive straight into pillar number 1, proactive roadway maintenance systems, or PRMS, which serves as the foundational data layer here.
Now, historically, infrastructure management was, well, highly reactive and plagued by massive latency. Think about it. City planners were literally waiting around for citizen complaints or relying on manual visual inspections. It could take weeks or even months to fix a pothole. But what we saw at WCX 2026 is a definitively proactive, predictive model. We're talking crowdsourced telematics, real-time edge AI alerts, and incredibly detailed 3D digital twins mapping roadway degradation as it happens. We're moving away from merely repairing broken assets and stepping into true life cycle stewardship.
A perfect example of this is the PRMS pilot from Honda and Drive Ohio. They essentially turned standard consumer vehicles, like a Honda CR-V, into distributed diagnostic tools. It works like this. First, the car's existing LiDAR and vision sensors scan the road for potholes, faded lines, or shoulder drop-offs while you're just driving normally. Next, all that fragmented data is instantly anonymized and aggregated right at the edge. And finally, it's pushed straight to cloud dashboards for municipal predictive maintenance. For us as engineers, this is a game changer. It stops those microtransient accelerations that absolutely destroy fuel economy and tire life. You're literally using the fleet to optimize its own physical operating environment.
Moving on to our second pillar, intelligent V2X service nodes. This is the communication conduit required to actually transmit all that intelligence seamlessly. So as we integrate these vehicles into the smart city, we hit a massive RF engineering roadblock, the highly congested 5.9 GHz Intelligent Transportation Systems band. Automotive engineers have to strictly manage fractional bandwidth limits and tightly control out-of-band emissions to meet the FCC's 2024 restrictions. If we don't nail this, our safety-critical V2X signals are either going to saturate the spectrum or just get completely drowned out by adjacent urban Wi-Fi networks. It is a massive signal integrity puzzle. And that brings up a brutal compromise for onboard unit design. You've got to tightly couple sleek aerodynamic styling with heavy electromagnetic shielding to guarantee signal integrity in these EMI-rich environments. The days of just slapping an antenna on the roof and calling it good are completely over. The whole vehicle body has to be engineered for optimal RF propagation, all while managing heat and aerodynamic drag.
All right, shifting gears to pillar 3, bidirectional charging, or V2G and V2X. This is all about energy and macro grid integration.
Turning EVs into active mobile grid storage units is a phenomenal concept, but mathematically, it's incredibly daunting. The Flex V2X project showed how to solve this using some really complex Q-learning algorithms. We aren't just plugging cars in and walking away anymore. This advanced AI dynamically calculates the absolute best charge and discharge cycles, basically turning every parked vehicle into an intelligent energy asset.
Let's break that math down a bit. In V2G, Q-learning calculates the optimal action, so exactly when to charge or discharge and for how long, based on a specific state. That state includes variables like your battery's current state of charge, real-time wholesale grid prices, and even forecasted renewable energy generation. The algorithm maximizes your long-term reward by balancing the macro grid's economic and energy demands against the physical and thermal limits of the vehicle's microbattery pack. It's honestly an exquisite balancing act.
And grounding this high-level theory in hard engineering data, the results are just stunning. These intelligent, Q-learning-driven V2G strategies have actually proven to reduce battery degradation rates by exactly 7.68 per mil, or parts per thousand, when compared to unregulated extreme fast charging. For fleet operators and OEMs sweating over warranty claims and battery longevity, this algorithmic approach isn't just an environmental win, it's a massive margin protector.
Which brings us to our fourth and final MES pillar, low-carbon construction materials. This grounds the entire cyber-physical system in its physical substrate.
Look, we simply can't build the digital roads of tomorrow using the carbon-heavy methods of yesterday. Traditional cement production alone accounts for nearly 7% of global greenhouse gas emissions. It's massively energy-intensive. What WCX 2026 made clear is the urgent demand for next-generation circular materials. We're talking about recycled asphalt pavements and really innovative composites like UBC-rammed earth. These have a vastly lower embodied energy footprint while offering superior operational resilience. Let's zoom in on that rammed earth technology for a second, because it is absolutely fascinating. When you take local soils and fortify them with industrial byproducts like fly ash, you aren't just slashing the carbon footprint, you're engineering a material with exceptional thermal mass and superior fire resistance. Just think about that contrast. We're deploying thousands of highly sensitive edge compute servers and V2X nodes along our highways. And the perfect passive cooling housing for all this digital infrastructure is essentially an elegant fusion of ancient dirt building techniques and cutting-edge material science. Brilliant, right? So, synthesizing these four distinct pillars, the data layer, the communication conduit, the energy grid, and the physical substrate, we arrive at our core strategic takeaway for this briefing.
Mastering the 2026 automotive landscape requires total cyber-physical integration, from the materials all the way up to the cloud. As our vehicles transform into mobile edge nodes and dynamic grid storage units, the supply chain and revenue models fundamentally change. Maintaining architectural sovereignty of the core technology stack, meaning the software, the data, and the energy flows, becomes a baseline requirement for operational continuity and margin protection. Basically, if you as an OEM don't control the stack, you're just going to become a hardware vendor in someone else's ecosystem.
To succeed today, you, the automotive engineer, have got to expand your purview. You have to start thinking like a civic planner, designing smart intersections, and like a utility grid operator, balancing megawatt loads. And that leaves us with a pretty provocative question to ponder. As these domains completely blur together, who truly controls the data and energy flow in this new ecosystem? Will it be the automotive engineers, the grid operators, or the civic planners? Whoever answers that question will define the next decade of mobility. Thank you for joining me for the Strategic Explainer. Keep innovating, and I'll see you in the next briefing.
Hey everyone, and welcome to this explainer. Look, as a senior technical strategy consultant working in this space every single day, I'm speaking directly to you right now, the highly technical automotive engineers, the system architects, the mobility leaders who are in the trenches navigating what is frankly an incredibly complex landscape. Our goal today is to really decode the massive integrated design and engineering paradigm shift that just absolutely dominated the 2026 SAE WCX in Detroit. We're going to look way past the usual hype of electrification, and we're going to dissect the raw, system-level engineering survival strategies you need for the software-defined vehicle era. To break this down efficiently, we're using a McKinsey-style, top-down, MESI blueprint. So, mutually exclusive, collectively exhaustive. Here's our map for today. First, the overarching engineering paradigm shift. Second, the shift-left virtualization strategy. Third, model-based systems engineering. Fourth, the digital twin hierarchy. Fifth, multidisciplinary design optimization. And finally, we'll synthesize the whole shebang into the future of mobility.
Okay, part 1, the engineering paradigm shift. Let's establish the macro context here, because the automotive industry is standing on a burning platform right now. We aren't just dealing with a simple power transition anymore, we're dealing with extreme regulatory flux, completely vulnerable supply chains, and a frankly skyrocketing level of complexity when it comes to software-hardware integration. Which naturally brings up a pretty critical question. Is the traditional linear V model of development actually dead in the SDV, the software-defined vehicle, era? Think about it. Historically, disciplines like powertrain, chassis, and body, they worked in their own little silos, right? And they only integrated late in the cycle. But with modern SDVs, man, any architecture flaws you discovered during physical integration are going to lead to catastrophic time-to-market delays. The penalty for late-stage failure is just way too high now.
You know, what's really fascinating is this exact phrasing straight from the WCX 2026 reports. They literally call this a theological shift from physical, mechanical-centric to highly integrated software-hardware development. I love that phrasing, theological shift. This isn't just some glossy management buzzword, it's a survival-level strategic imperative. If your team is still optimizing individual components instead of system-level performance, honestly, your architecture is already obsolete.
And the structural difference between the old way and the new way is basically night and day. In the legacy setup, you've got a distributed ECU architecture. It's highly fragmented across dozens of nodes, and the software is tightly coupled to very specific hardware. It's incredibly rigid. But contrast that with the centralized SDE architecture. That relies on decoupled high-performance compute clusters utilizing hardware abstraction layers. That decoupling right there, that is the exact mechanism that frees us up to run engineering cycles in parallel.
All right, moving into part 2, shift-left virtualization strategy. This is our first real MES technical pillar, and it's all about process execution. Because you've decoupled software from hardware, you absolutely have to validate your software before the physical hardware even exists. So how do we actually pull that off? We do it through virtual development kits, or VDKs, like the one Synopsys introduced for ARMs and compute subsystems. VDKs are a total game changer because they let you completely eliminate hardware wait times. You are literally verifying software months, sometimes years, before physical silicon is ever minted. It gives you massive systemic risk hedging, lets your global teams collaborate on one standardized virtual platform, and crucially, it finally enables real CI/CD, continuous integration and continuous deployment pipelines in automotive engineering.
That brings us to part 3, model-based systems engineering. Now that we have the process execution defined, we need the architectural framework to actually break down those old-school engineering silos. MBSC is what transitions your engineering org from using passive, static documentation tools into an active, self-verifying engineering platform. It literally becomes your single source of truth. And a huge push at WCX 2026 was the need for standardized data ontologies. Basically, this means proprietary subsystem models from your Tier 1 and Tier 2 suppliers can be seamlessly plugged straight into an OEM's master dynamic simulation environment. And you do it without losing an ounce of data fidelity or dealing with constant translation errors. It just works.
Okay, part 4, the digital twin hierarchy. Building directly on top of MBSE, we transition to our third pillar, which is all about dynamic validation. Look, we all know modern digital twins aren't just pretty 3D pictures anymore, right? They actually follow a specific evolution. They start their life as static CAD models. Then they level up to high-fidelity physical alignment, gathering lab and field data. And finally, they evolve into full bidirectional real-time control twins that synchronize perfectly with the physical asset in the real world. This creates a continuous digital thread across the entire product lifecycle. We are moving away from reactive maintenance and stepping into true predictive capabilities.
But we've got to be super rigorous here. WCX 2026 made it crystal clear. We are officially entering the era of the physics-informed digital twin. It is no longer enough to just have data-driven machine learning models. Your AI absolutely must align with physical reality. Researchers showed this off with frameworks like Alpha PM, which gives you spatially resolved fuel cell dynamics. By aligning digital outputs with trusted legacy tools, things like CFD and finite element analysis, engineers can run entirely zero-risk what-if analyses for extreme operating conditions. And you do it without blowing up prototypes that cost millions of dollars.
Next up, part 5, multidisciplinary design optimization. Let's transition to our final technical pillar, which is achieving system-level resolution through MDO.
In modern SDV architecture, you're constantly battling conflicting constraints, right? Mass reduction versus crashworthiness, battery packaging versus chassis stiffness. It's a headache. MDO solves this by optimizing all these complex interactions simultaneously. But I have a rapid-fire question for you. Why does the automotive industry heavily prefer single-level MDO, while the aerospace guys almost always default to multi-level MDO?
The answer is pure practicality. Automotive development cycles are brutal. They are incredibly fast. Centralized single-level optimizers minimize all that cross-team coordination overhead and ensure a much faster convergence toward a feasible solution. Aerospace has these highly autonomous design groups stretching their work over decades. Auto needs speed, period.
Looking at the different architectures, single level is super fast and great for structural sizing. Multi-level works well if you've got really complex EE systems spanning multiple suppliers. But I really want to highlight the meta-model-based approach. Modern automotive design spaces are massively high-dimensional. It's like a giant puzzle. By using advanced proxies like Kriging metamodels or active learning, we can take thousands of hours of heavy simulation time and compress it into near-instantaneous feedback. For things like NVH and crashworthiness, that is a complete game changer. To really land the real-world impact of this AI-driven MDO, just look at this number. By applying these optimization frameworks to a conceptual wheel design, researchers at the Congress achieved a 5% mass reduction. But the crazy part? They coupled that mass drop with a staggering 30% increase in lateral stiffness. So this isn't just basic lightweighting anymore. This is actively retuning the fundamental structure for massive noise, vibration, and harshness enhancements.
Which brings us to part 6, the future of mobility. Let's synthesize everything we've talked about, our 4 technical pillars, into a cohesive view of where this is all actually going.
The ultimate takeaway here is pretty undeniable. Integrated design is no longer just some localized efficiency initiative to save a few bucks. It is a core strategic imperative for global competitiveness. The winners in 2026 and well beyond are going to be the organizations that finally break down their internal silos and achieve absolute digital continuity, literally from initial styling right through to post-production support.
So, synthesizing our strategy today? Number 1, you must shift left to pull your validation into the virtual realm years before physical hardware is even a thought. Number 2, you must secure your SDV architectures using robust, decoupled middleware. And number 3, you have to maintain that unbroken digital thread across the entire lifecycle, leveraging physics-informed AI to ensure your optimization actually matches reality.
Which leaves us with a real gut-check question for every single engineering executive tuning in to this explainer. As you evaluate your own development pipelines today, ask yourself, in the software-defined vehicle era, is your engineering architecture actually achieving true digital continuity, or are you just heavily optimizing your legacy silos? The technology to integrate everything is literally right here. The only barrier left is organizational execution. Thanks so much for joining me on this deep dive into the SAE WCX paradigm shift. See you next time.
Welcome to this Strategic Explainer. I'm stepping into my role today as your Senior Tech Strategy Consultant to unpack the absolute critical materials and lightweighting paradigm shifts emerging right out of the 2026 SAE WCX. Look, if you're architecting the vehicles of tomorrow, you already know that cutting mass isn't just about efficiency anymore. It's literally about survival in a software-defined, carbon-accountable era. So let's dive right into this.
Applying a top-down McKinsey-style framework, we're going to deconstruct the entire lightweighting landscape into 5 mutually exclusive and collectively exhaustive, or MEIS, pillars. We've got the systemic paradigm, 3rd-gen AHSS metallurgy, gigacasting integration, cell-to-chassis architecture, and finally, bio-based and recycled composites.
All right, let's jump straight into part 1, the systemic lightweighting paradigm. So why are we rethinking every single gram of material in modern vehicle architecture? Well, it really comes down to this massive number, 500 kilos. The shift toward electrification has just completely upended how mass is distributed across a vehicle. Premium EV battery packs introduce this insane mass penalty that can easily exceed 500 kilos. And that doesn't just eat into your range. It fundamentally alters the vehicle dynamics, it piles onto the load requirements for suspension systems, and it severely restricts payload capacities, especially in heavy-duty applications. Because of that reality, the legacy V model of isolated component optimization, that's completely dead. You can't have the powertrain team, the chassis team, and the body team all working in their own little silos anymore. In 2026, lightweighting is a systemic, multidisciplinary exercise. It is intrinsically linked to lifecycle sustainability and software-defined architectures. We essentially have to shift left, bringing virtualization and simulation into the very earliest phases of design just to balance out these extreme mass constraints.
Moving right along to Section 2, 3rd-generation AHSS metallurgy.
Despite all the buzz around exotic composites, steel remains the absolute backbone of automotive construction, primarily because it's cost-effective and the supply chain is just incredibly mature. And here is the real so what of third-generation advanced high-strength steels. It's all about that stark contrast in elongation. Traditionally, if you wanted gigapascal-level tensile strength, like the 1500 megapascals in press-hardened boron steel, you had to sacrifice ductility, dropping down to a super brittle 5 to 8% elongation. That meant using highly energy-intensive hot stamping. But third-gen AASS, it hits massive tensile strength while holding on to a 15 to 20% elongation. This is a massive game-changer, guys. It allows for energy-efficient cold stamping of highly complex safety structures, entirely bypassing the huge capital and energy costs of hot stamping facilities.
So what's the metallurgical magic making this possible? It's all about microstructural manipulation. Engineers are stabilizing retained austenite at room temperature using tightly controlled quenching and partitioning, or trip cycles. When a crash happens and the steel deforms, that austenite physically transforms into martensite. This transformation literally absorbs immense crash energy and gives you a super high strain hardening rate. It's absolutely perfect for critical impact zones, like your B-pillars.
But of course, there's an engineering bottleneck we have to navigate, and that's edge cracking sensitivity. Gigapascal-grade steels have notoriously terrible edge ductility. If you run conventional mechanical punching on these metals, you're going to get a really dismal hole expansion ratio, or HER, of below 12%. However, WCX data proves that if you leverage advanced edge preparation techniques, specifically laser cutting or electrical discharge machining, you can astonishingly push that HER from 12% to over 100%. Master the edge prep, and you immediately unlock the deep draw geometries that modern styling and safety standards absolutely demand.
Okay, let's pivot to Section 3, gigacasting or megacasting integration. Shifting gears from ferrous to non-ferrous metals, gigacasting is totally rewriting the rules for the body in white. By integrating dozens of individual stamped and welded parts into a single massive aluminum cast structure, OEMs are just slashing their bill of material complexity and really tightening up physical tolerances. But when we try to align this with incredibly strict carbon mandates, a massive chemical challenge pops up, actually using sustainable secondary or recycled aluminum in the mix.
As OEMs aggressively push to use low-carbon, recycled aluminum to hit their green targets, iron impurities quickly become public enemy number one. In these massive structural castings, excess iron threatens to completely compromise the ductility of the component, which leads to catastrophic structural embrittlement. Obviously, you simply cannot have a brittle suspension or subframe casting. It's a non-starter.
The metallurgical solution presented at the Congress is actually pretty elegant. It's the precise addition of manganese. By adding it straight into the recycled aluminum melt, chemists can literally force the iron impurities to change their physical shape. It transforms the brittle, needle-like beta phase iron structures into totally benign, script-like alpha phases. This slick chemical intervention allows the secondary alloy to tolerate up to 0.44 weight% iron without suffering any structural failure whatsoever, finally unlocking true circularity in gigacasting.
Moving to Section 4, cell-to-chassis architecture.
Building on this whole concept of large-scale integration, we are effectively looking at the death of the traditional battery module. Cell-to-chassis or cell-to-body architecture represents the ultimate structural convergence. We are completely eliminating the dead weight of intermediate module housings and forcing the battery enclosure itself to step up and act as the primary load-bearing floor pan of the vehicle.
Now, the crucial takeaway here is that this is not just about saving space. Yes, for sure, it maximizes gravimetric and volumetric energy density, but fusing a high-density battery array directly into the body in white drastically shoots up the overall chassis torsional rigidity. That means better handling dynamics and seriously enhanced noise, vibration, and harshness metrics. And what's truly mind-blowing, as highlighted by Tymon Niedezak's award-winning WCX research, is that these enclosures are evolving way beyond passive structures. They're utilizing multifunctional composites that embed real-time stress and thermal sensors directly into the chassis material itself. We're talking about a literal self-health monitoring floor pan.
And that brings us seamlessly to our final MECE pillar, Section 5, bio-based and recycled composites. In 2026, lightweighting has to be evaluated through the lens of life cycle assessment. You just can't ignore it. To achieve true circularity and dodge future carbon taxes, the industry is executing a super aggressive pivot away from traditional thermoset plastics. You see, thermosets undergo irreversible chemical cross-linking. Once they're formed, they cannot be unformed, which makes them practically impossible to recycle at the end of their life. So the massive shift right now is toward high-performance thermoplastic composites like fiber-reinforced polyamides and PEEK, because these can be melted, reformed, and completely repurposed, finally closing that material loop.
When you look at the sustainability life cycle data extracted from the SAE Congress, it is crystal clear why OEMs are transitioning so hard toward post-consumer recycled blends. It is all about satisfying that cradle-to-grave emissions accounting. Using fossil-based virgin plastics carries this massive embodied carbon penalty that OEMs simply can no longer afford to carry on their balance sheets.
The impact of closing that material loop is absolutely staggering. In fact, studies presented at WCX demonstrated that utilizing a 50-50 blend of virgin and post-consumer recycled PLA and PHA bioplastics achieves an incredible 57% reduction in global warming potential. And the best part for you engineering teams out there, this massive carbon reduction is achieved without sacrificing an ounce of the functional durability or mechanical integrity of the component.
But wait, it's not just the plastic matrix that's evolving, the reinforcements are getting an upgrade too. Researchers are having huge success replacing carbon-intensive synthetic glass and carbon fibers with highly renewable natural alternatives, things like bamboo, jute, and flax. These biological fibers offer superior specific mechanical properties purely because of their incredibly low density. And here's a totally fascinating, kind of surprising engineering bonus from the research. These natural fibers actually provide outstanding modal damping characteristics. This makes them vastly superior for next-generation acoustic panels and vibration damping in both EV and high-efficiency internal combustion cabins.
So, as we transition into this software-defined, carbon-accountable future, the goalposts haven't just moved, they're in a completely different stadium. The ultimate question for automotive leadership remains, are you simply cutting weight in isolated silos, or are you architecting true systemic sustainability? Thank you so much for joining me for this strategic explainer. I really challenge you to take this holistic paradigm back to your engineering teams today.
All right, let's jump straight into this explainer. Today, I'm putting on my hat as a senior technical strategy consultant to deconstruct a massive, frankly unprecedented paradigm shift happening right now at the intersection of automotive and defense engineering. We're going to completely tear down the technological evolution of military ground vehicles. And we're doing this using some incredible deep dive insights pulled straight from the 2026 SAE WCX in Detroit. Look, the line between commercial automotive innovation and specialized defense engineering, it isn't just blurring anymore, it is practically vanishing. And if you're an engineer in the mobility space today, missing this shift means you're engineering for a past that literally no longer exists. To analyze a shift this massive, we're applying a strict top-down MEC framework, mutually exclusive, collectively exhaustive. We're going to hit the overarching paradigm, the advanced combat engine, signature management, aluminum alloys, and finally, how it all synthesizes into the integrated combat ecosystem. Okay, Section 1. Let's look at the geopolitical context and the macro-level architecture that's fundamentally redefining mobility on the battlefield. So, the crucial takeaway right off the bat is that modern vehicles are no longer just heavy, isolated hardware platforms. They've completely transformed into highly interconnected, software-defined lethality nodes. In the past, you'd have a military vehicle with dozens of isolated electronic control units, right? Each ECU doing one hyper-specific thing. It was heavy, it was complex, and honestly, it was incredibly rigid. But today, we're moving aggressively towards software-defined vehicles, or SDVs. We're talking centralized computing architectures, high-performance computers, secure over-the-air updates, the whole 9 yards. This drastically optimizes what we call SWAC, space, weight, and power. But, and this is a big but, the trade-off is that this new architecture requires absolutely immense computational power to process real-time AI targeting, complex sensor fusion, and active protection systems all at the same time. And here is the rub. All that critical software requires extreme electrical loads. More computing power and more active sensors inevitably mean more heat and more mass. And that right there brings us to our primary thermodynamics and materials physics puzzle. As the source material so brilliantly puts it, in the modern era of high-precision adversarial sensors, being hard to find is as important as being hard to kill. Let's be real, you simply cannot be hard to find if your core electronic systems are radiating massive thermal blooms like a beacon.
Moving to Section 2, the Advanced Combat Engine. How exactly are engineers solving that immense power generation problem without creating massive, glaring thermal vulnerabilities?
Well, enter the U.S. Army's Advanced Combat Engine, or ACE. This thing is a total game changer for propulsion. It utilizes an opposed piston diesel architecture. Picture this, 2 pistons per cylinder moving directly toward each other. By executing this specific design, engineers have completely eliminated the cylinder head and the valve train. If you know engine design, you know those 2 components are massive thermal liabilities and just dead weight. Stripping them out entirely is such an elegant, almost brutalist piece of engineering.
And the tactical advantage here is undeniable. This opposed piston architecture achieves a staggering 50% increase in power density over current state-of-the-art combat engines. 50%. You're getting vastly more power out of a much smaller physical footprint. And that instantly frees up vital internal volume for larger battery packs, thicker structural armor, or just way more payload. But wait, it gets better. More importantly for survivability, it delivers a 20% reduction in heat rejection. Think about what that means strategically out in the field. Less heat rejected by the engine block means you can run significantly smaller cooling systems and much smaller radiators. That directly shrinks the vehicle's vulnerable cross-section and vastly lowers its infrared signature. It's a perfect example of foundational thermodynamics directly answering a high-stakes technical imperative. So that leads us perfectly into Section 3, silent mobility and signature management. Thermal evasion is an absolute necessity now. You see, you've got the significantly more efficient engine, sure, but you still have massive battery packs and high-performance computers generating intense heat. You can't just guess and check your way out of this. To manage these thermal outputs, engineers leverage a highly advanced 3D fluid dynamics simulation tool called MUSIS. Way before a single piece of physical steel is ever bent or welded, they use this tool in a virtual environment to precisely map out convective heat transfer and external wind flow over the hull. It allows them to actively optimize exactly where they place high heat power electronics, ensuring the exterior surfaces stay strictly within safe ambient temperature thresholds.
And here is where the hybrid electric drivetrain literally becomes a weapon. Look at this data on thermal contrast. Shifting from standard combustion into what they call silent mobility mode, which means operating purely on battery power, dramatically slashes the detection risk. The vehicle's thermal contrast against the ambient background drops to basically minimal levels. It's high-grade acoustic and thermal stealth, surprisingly achieved by strictly adapting commercial electric vehicle technology for the battlefield. Now for Section 4. Because, let's face it, evasion is never foolproof. When stealth inevitably fails, physical survivability has to instantly take over.
If you're going to pack a ground vehicle full of heavy batteries and hybrid electric drives, you have to aggressively save weight somewhere else. But you absolutely cannot compromise the crew's safety. Because of this, the entire metallurgical paradigm is shifting overnight. We're rapidly moving away from traditional, heavy, rolled homogeneous steel. The new standard? Advanced high-strength aluminum alloys. These are the exact same materials that have seen massive R&D investment in the commercial automotive space to increase EV range. Now they're being rigorously adapted to offer equivalent ballistic protection for defense platforms, but at a fraction of the mass.
And I want to be clear here, this lightweighting, it's not just about making the vehicle a little faster or slightly more agile. It is a strict systemic mandate. Shedding mass in the hull structures, the suspension systems, and the tracks is an absolute necessity just to offset the crushing weight of those massive battery packs and active defense systems we just talked about. Plus, it has this incredible secondary benefit of drastically improving operational fuel consumption and extending the life cycle of those mechanical components in the dirt. But here's a crazy question. How do you actually know if this advanced, lightweight aluminum armor is still protecting you after taking a direct hit? The answer is Sensor-Enhanced Armor, or SCA, and this is just wild engineering. The integrated system constantly emits ultrasonic pulses directly into the solid armor plate. It then takes that acoustic response and compares it back to a mathematically perfect baseline. If there are any microcracks, deep delaminations, or structural compromises, it instantly alerts the vehicle's digital twin and the human operators. You guys, it is literally armor that can self-diagnose battle damage in real time.
All right, Section 5. Let's bring all these MEC pillars back together into a cohesive view of the future integrated combat ecosystem.
How does this all synthesize in an active theater? Well, the future military ground vehicle seamlessly integrates at opposed piston power, the thermal stealth management, and those lightweight self-diagnosing alloys directly into a virtual digital twin environment. This fundamentally revolutionizes predictive maintenance.
By feeding real-world physical sensor data straight into a high-fidelity digital twin, the overarching system can simulate thousands of operating cycles in seconds. It accurately predicts when a critical component is going to fail long before it actually does. This strictly optimizes global supply chains and ensures these highly complex vehicles are actually ready for rapid deployment when it counts.
So, I'm going to leave you with this final, somewhat provocative thought. The developments showcased at the 2026 SAE WCX clearly prove that the military is actively pivoting to open software standards, live digital twins, and dual-use thermodynamics just to survive. They are systematically adopting commercial engineering practices to achieve absolute tactical dominance. So looking at your own commercial projects, are your future mobility architectures engineered to be just as resilient against the multi-domain threats of tomorrow? Thanks for joining me on this explainer, and keep pushing the boundaries of what's possible in vehicle engineering.
Let's kick off this executive explainer. As your senior technical strategy consultant today, we're tearing down the massive 2026 SAE WCX Symposium. For those of us living and breathing professional automotive engineering, the Detroit WCX Congress is literally ground zero for mobility innovation. We're applying a strict, top-down McKinsey framework today to prove one absolutely crucial point. Motorsports isn't just some marketing exercise anymore. It's the definitive, high-stakes laboratory for global automotive engineering. Let's get right into it.
To filter through the hundreds of technical papers, we're taking a strict MISI approach. That's mutually exclusive, collectively exhaustive. Here is how we're segmenting these innovations. First, motorsports as the ultimate innovation crucible. Second, the high-performance path for hydrogen internal combustion. Third, optimizing for aerodynamic wake rules. Fourth, advanced manufacturing prototypes. And finally, the engineering trajectory leading up to 2030.
Starting with Section 1, Motorsports as Innovation Crucible, where we're stress testing the future of mobility.
This quote straight from the Congress proceedings really hits the nail on the head for our strategic so what here. Look, we're moving past the unbridled hype of pure battery electric vehicles and stepping into this era of technology-neutral pragmatism. The track is where commercial tech, whether that's advanced internal combustion, hybrid systems, or software-defined architectures, has to prove absolute resilience under extreme physical loads before it ever touches a consumer highway.
The ultimate catalyst here is the 2026 FIA technical regulations. This is a total paradigm shift. Historically, as you know, aerodynamicists operated in silos, optimizing a front wing or a diffuser totally in isolation. But these 2026 rules force a transition to integrated component wake rule system synergy. Every single design decision now has to be mathematically evaluated against its aerodynamic wake impact, that dirty air, on the vehicle following it. You aren't just designing for your own car anymore, you're literally engineering the air for the car behind you.
Let's move to our first technical pillar, Section 2, H2ICE, High Performance Path, Pushing Thermodynamics to the Limit.
So this is where internal combustion is actually seeing a massive renaissance. To hit zero emissions without dragging around the massive weight penalty of battery packs, engineers are pivoting hard to hydrogen internal combustion. But we hit a physics problem. To avoid extreme NOx emissions, you have to run these engines incredibly lean. We're talking ultra-lean mixtures with lambdas of 2.0 to 2.2. A traditional spark ignition completely fails here. It just misfires. So what was presented at WCX? Engineers are deploying active pre-chambers. They inject a tiny volume of fuel into a separate microchamber, ignite it, and blast high-pressure plasma jets into the main cylinder. That instantly ignites the ultra-lean mixture. It's brilliant.
Just look at the sheer thermodynamic breakthrough in these top-row metrics. By combining those active pre-chambers with Miller's cycle valve timing, and frankly, a massive 282 kilopascals of boost pressure to make up for the power density drop, they're crossing the holy grail threshold. Over 50% indicated thermal efficiency with virtually zero NOx, consistently below 50 parts per million. For spark ignition thermodynamics, this is the absolute zenith.
Next up, Section 3, Aerodynamic Wake Rule Optimization, focusing on fluid dynamics and efficiency. So how do we master these new FIA constraints? Notice the extremely strict geometrical limits we're dealing with. Regulators are forcing a minimal convex curvature of 25 millimeters on base plates specifically to suppress those powerful, dirty air-generating vortices. And simultaneously, under massive aerodynamic loads, the floor plate is legally capped at a maximum deflection of just 8 millimeters. You are boxed into this microscopic window of structural flexibility. And why does an 8 millimeter deflection limit matter so much? Because when we map out the downforce generation for the 2026 vehicle, the floor plate and diffuser absolutely dominate. They're responsible for a staggering 58% of total downforce. Ground effect is literally everything right now. Underbody airflow management is the definitive battleground, which means keeping that floor geometrically stable at 300 kilometers per hour is your priority number one.
Since the macro geometry is so tightly locked down by regulations, the real competitive advantage has shifted to microaerodynamics. For instance, WCX papers show that installing microspoilers, just 5 millimeters tall, on the sides of the tires cuts wake interference by 15%. That 15% reduction, that's the difference between a totally stalled underbody and a perfectly stable downforce platform when you're hitting high-speed corners.
To process wake structures this complex, traditional CFD is just hitting a wall. Standard Navier-Stokes-Rans models? Too inaccurate for massive flow separation. Pure large eddy simulation? Computationally bankrupting. So instead, teams are migrating to wall-modeled large eddy simulation, WMLES, accelerated by massive GPU clusters. On top of that, they're deploying NVIDIA Domino AI surrogate models. This predicts aerodynamic drag and lift in milliseconds instead of days. For all intents and purposes, AI is the new wind tunnel.
Moving on to Section 4, Advanced Manufacturing Prototypes and Structural Realization.
Once your AI designs the perfect aerogeometry, how do you actually physically build it to survive those brutal 8mm deflection limits? The workflow has evolved into a hyper-fast, closed-loop process. Step 1. AI simulation dictates the topology. Step 2. Move straight into advanced additive manufacturing, totally bypassing traditional tooling. Step 3. Close the loop with high-density LiDAR point cloud validation. Forget old photogrammetry. Real-time LiDAR lets engineers perfectly map the dynamic, physical flexing of carbon fiber right back into their CFD software.
Executing this physically relies 100% on next-generation material science. To meet those FIA floor stiffness rules, teams are using aerospace-grade titanium AMS 4928 for floor stays and pairing that with ultra-rigid 2mm carbon fiber reinforcements. But it goes beyond composites. We're now seeing the direct 3D printing of structural components with built-in thermal management microchannels. You are literally printing the radiator directly into the chassis. It's wild.
Finally, Section 5, the 2030 Engineering Trajectory, bringing it all together with systemic integration.
So, how does all this extreme track data actually impact the global commercial market? If we look down the macro timeline, the tech transfer is immediate. By 2027, that ultra-lean hydrogen combustion and active pre-chamber tech we just talked about, that's going straight to heavy-duty commercial fleets, trucks that simply can't afford massive battery weight. By 2028, those AI proxy models will drive consumer software-defined vehicles, enabling real-time chassis updates over the air. And by 2030, the integration of 450 watt-hour per kilogram solid-state batteries is going to power autonomous swarm racing. That will completely redefine machine perception and vehicle dynamics as we know it.
Which leaves us with this final, somewhat provocative thought. We're stepping into an era of absolutely merciless engineering optimization. The math is exact, the regulations are suffocating, and the AI is relentless. So, as the line between digital simulation and track reality completely blurs, you have to ask yourself, in your next development cycle, are you merely engineering for regulatory compliance, or are you engineering for absolute victory? Keep that in mind as you head back to your design frameworks. Thanks for joining me for this explainer.
All right, let's jump right in. Welcome to this explainer. I'm stepping into the role of your lead technical strategy consultant today, and we are embarking on a really focused McKinsey-style top-down deep dive. We're looking at the advanced safety technology trends coming straight out of the 2026 SAE WCX World Congress. Now, if you're a senior automotive engineer, this analysis is tailor-made for you. We're skipping the basic fluff and looking right past the hype to deconstruct the exact technical mandates you need to build the next generation of software-defined vehicles. So let's get into it because we're moving fast and going deep into this converged safety architecture paradigm. To keep this strictly MEIS, mutually exclusive and collectively exhaustive, here is our agenda. 1. The architectural shift. 2. Behavioral safety, specifically looking at SOTIF. 3. System security and cybersecurity. 4. Data integrity, focusing on trust management. And 5. The safe system approach.
Okay, Section 1. The architectural shift, SDVs and zonal HPCs. Let's be real for a second. The fundamental reality we're facing is that those legacy distributed ECUs, they're dead. Traditional safety frameworks are literally collapsing under the weight of modern vehicle design.
We're in the middle of this massive transition from dozens of isolated little boxes to centralized zonal architectures, where your sensors and actuators act as regional data hubs. And those hubs are being linked via multi-gigabit automotive Ethernet backbones straight to high-performance computers. When you take that massive integration complexity and smash it together with multi-pathway propulsion systems and these crazy advanced AI perception stacks, you create an environment where treating hardware, software, and safety as separate silos is frankly an engineering impossibility.
Section 2, Pillar 1, Behavioral and Operational Safety.
So, the foundational pillar of modern vehicle safety isn't just about preventing a random short circuit anymore. It's about behavioral and operational safety, which means we need to talk about SOTIF, or ISO 2148. And I really want you to reframe SOTIF in your mind right now. Do not look at this as just another regulatory burden. It is an absolutely crucial engineering blueprint for managing functional insufficiencies. SOTIF is specifically built to handle the hazards that pop up from performance limitations and unexpected triggers within the vehicle's ODD, or operational design domain. It uses this really strict sense plan act model to make sure that even if your system executes its code perfectly, it doesn't accidentally cause a catastrophe just because it hit an environmental edge case. And I think this brilliantly illustrates the exact boundary between legacy compliance and what we're actually dealing with today. Over on the left, you've got ISO 26262 functional safety, which is laser focused on mitigating discrete hardware or software faults. Great. But what happens when there is zero fault? I mean, imagine a perception module that is technically functioning flawlessly, rated QM under ISO 26262, but it entirely misses a pedestrian because of some weird lighting glare or heavy rain. There's no malfunction. The system didn't break. Yet the hazard is massive. That right there is the exact gap where SOTIF has to step in, focusing entirely on those perception gaps and ODD limitations when the underlying system is completely healthy. Section 3, Pillar 2, System and Digital Security. Now, what's really fascinating here is how these specific cybersecurity standards are practically forcing our hands at the architectural level. Take a look at ISO/SAE 21434. Alongside the core principles of SAE J3061. They are literally mandating the integration of cybersecurity directly into your software development lifecycle. And then, look at SAE J1939-90C. Because we're all moving toward these heterogeneous operating systems, running RTOS, Linux, and QNX all on the exact same platform, we have to validate incredibly robust ECU authentication and cryptography way early in the design cycle. We're talking about managing cryptographic operations across super diverse protocols, from standard CAN to DWIPE and SOAMS/IP. Listen, if you don't engineer this right at the root level, your entire zonal architecture is just one giant open attack surface. But how do you actually execute that level of security without absolutely tanking your development pipeline? Well, WCX 2026 highlighted a real game changer, the Mosaic Tara methodology. This is how we finally ditch those redundant, manual, asset-centric risk assessments. The workflow is actually quite elegant. First, you decompose these complex vehicle systems into manageable functional modules. Second, you assess those modules completely independently. Third, and this is the kicker, you reuse those threat analysis and risk assessment results across different functional domains and even different vehicle platforms. And finally, you aggregate the whole thing for comprehensive risk prioritization. Modularity is quite frankly the only viable way to efficiently secure the recurring assets you're going to find in these complex zonal setups.
Section 4, Pillar 3, Network and Data Integrity.
As our vehicles start making split-second autonomous decisions based on external V2X communications, data integrity becomes the absolute paramount factor for safety. We are far beyond just talking about privacy here. We are talking about preventing network spoofing that could trigger false hazard braking or jam your sensors. The technical requirements for trust management protocols are non-negotiable. You absolutely need proxy-based security gatekeepers. You have to implement elliptic curve-based multi-party key negotiation to guarantee rock-solid ECU authentication. At the hardware level, that means redundant sensors with multimodal fusion just to cross-verify the external data you're pulling in. And on the infrastructure side, we're looking closely at blueprints like the Drive Ohio NEVI oversight framework to lock down the electrical grid, especially as these vehicles basically turn into mobile energy storage units.
Section 5, Synthesis, the Safe System Approach.
So, tying this all together into a unified strategic mandate, the crucial takeaway is perfectly summed up by this insight from the Congress: maintaining architectural sovereignty. You just cannot treat functional safety in cybersecurity as isolated domains anymore. It doesn't work. As engineers, we have to implement highly collaborative, shift-left design strategies. You have to validate earlier and utilize merged processes like Sahara, which brilliantly integrates safety and security hazard analyses together. Think about it. If a cyber vulnerability can blind your SOTF perception stack, your functional safety rating is literally meaningless. The whole thing has to be engineered as one continuous sovereign stack. Which leaves us with the ultimate engineering reality check. I want you to honestly evaluate your current systems. Look at your workflows, your testing environments, your team structures. Are they still operating in silos? Is your development pipeline actually integrated enough to support this converged safety mandate? The transition to the software-defined era is absolutely ruthless to legacy processes. Embracing these integrated intelligence practices isn't just about ticking a regulatory box. It is the fundamental baseline for survival in today's automotive industry. So take these frameworks, bring them back to your teams, challenge your existing architectures, and start building for 2026 and beyond. Thanks for joining me for this explainer.
All right, let's dive straight into this explainer. As a technical strategy consultant, I want us to really unpack the macro-level paradigm shift we just saw come out of the 2026 SAE WCX in Detroit. We are looking at a fundamental recalibration of smart manufacturing, specifically how it's evolving to support software-defined vehicles and, of course, multi-pathway propulsion. To deconstruct a landscape this complex, we're going to apply a strict top-down MEIS framework, mutually exclusive, collectively exhaustive, breaking down the ecosystem so we can see exactly what this means for your production strategies moving forward. Here is our roadmap for today. We'll start with the smart manufacturing strategic paradigm, then break down our 3 core pillars: cyber-physical production systems, industrial 5G and edge, and flexible powertrain assembly lines. Finally, we'll wrap with the 2026 manufacturing strategic outlook. Before we even touch those core pillars, we absolutely have to establish the prerequisite, and that's the unified digital backbone. Look, manufacturing is no longer about deploying isolated Industry 4.0 tools. Those days are gone. With modern vehicles carrying literally tens of gigabytes of software, you absolutely require a unified digital thread, one that flawlessly connects your design simulation directly to the physical factory floor to handle that exponential complexity.
Let's move right into our first core pillar: cyber-physical production systems.
Think of this as the brain of the operation. We're looking at the evolution of the digital twin cyber-physical production system, or DTCPPS. Notice the hierarchy here moving up the stack. We're completely shifting away from just managing discrete singular components, like a single sensor or a traction motor. Instead, we're orchestrating composite twins for entire assembly cells. And at the absolute top tier, the shop floor level, we aren't just monitoring things anymore. The system is autonomously rescheduling across the entire physical and virtual plant to optimize system-wide efficiency. It's a complete, living operational mirror.
Now, here is the real game changer. It's the shift from traditional numerical solvers to agentic AI. Previously, you had engineers manually writing code requests to solve static physics models, right? Well, agentic AI leverages generative world models. What that means is the system can proactively reason. It autonomously identifies an efficiency gap on the line, figures out the solution using physics-informed models, and actually executes the corrective actions in real time. It completely closes the loop without any human intervention. It literally transforms a factory from simply being automated to being truly autonomous. Next up, we're exploring the nervous system of our framework: industrial 5G and edge computing. To actually enable that kind of high-level intelligence, industrial 5G and edge computing have to work in perfect tandem. You just can't rely purely on cloud infrastructure anymore. It introduces unacceptable latency for what we're trying to do. High-bandwidth 5G combined with edge computing brings massive data processing directly to the production cell. And for real-time safety and automation, that is an absolute non-negotiable. Let's dig a little deeper into that edge processing. By localizing compute power directly onto your manufacturing assets, using ruggedized Linux platforms like Quasar Edge, OEMs guarantee deterministic data handling. Think about it. When you are synchronizing thousands of robotic arms and autonomous mobile robots at the exact same time, you literally cannot afford the fatal risks of packet loss or signal jitter. Edge AI ensures those machine learning models execute instantly, maintaining absolute real-time precision on the floor. So what does the software-defined architecture actually do to the physical factory floor? Well, legacy systems relied on distributed ECUs and incredibly complex point-to-point wiring, with software just kind of flashed at the very end of the line. But today's software-defined vehicles, utilizing simplified 48-volt zonal backbones, force a complete architectural layout change. Your assembly lines must now handle highly sophisticated software flashing and hardware-in-the-loop virtual validation at every single stage of production,
running completely in parallel with the physical hardware integration. Let's move to the muscle of the operation, flexible powertrain assembly lines. Now we get into the physical execution. The reality coming out of WCX 2026 is a massive, and I mean massive, resurgence in hybrid and advanced internal combustion engine technologies. And navigating this volatile multi-pathway propulsion landscape demands incredible agility. By utilizing advanced autonomous mobile robots, your factories have to seamlessly pivot. One minute you're assembling battery electric models, the next it's complex hybrid systems wedding motors to engines, and then it's next-generation ICE platforms, all happening dynamically on the exact same line. To really grasp the sheer physical challenge this presents, just think about this metric: pushing past 50% indicated thermal efficiency. Achieving this massive breakthrough via ultra-lean combustion, say at a lambda of 2.0, means your factory machining tolerances for cylinder temperatures and fuel delivery have to be pushed to absolute microscopic limits. It's an incredible engineering feat for sure, but it means your flexible machining centers must handle this extreme ICU precision one moment and then completely switch gears to milling structural EV battery enclosures the next.
Which brings us to our final section, the 2026 Manufacturing Strategic Outlook.
So, pulling this all together, synthesizing these pillars, the organizations that are going to dominate the remainder of this decade share a few core traits. They've unified that digital backbone, connecting design and production. They've adopted edge-first intelligence for low-latency quality assurance. They are operationalizing sustainability through integrated lifecycle assessments directly on the line. And they have fully embraced extreme manufacturing agility. The takeaway here? Engineering teams have got to stop viewing the factory floor as just a static cost center. It is an integrated, software-defined testing ground that is absolutely crucial for protecting your architectural sovereignty against macroeconomic volatility. And that brings us to the ultimate question you need to be asking your engineering teams as you architect your strategy. Is your production ecosystem actually agile enough to survive the multi-pathway propulsion era? Do you have the digital continuity and edge intelligence required to lead, or are you still relying on rigid legacy architectures? The blueprint for success is already being written. Thanks for joining me on this explainer, and keep innovating out there. Hey everyone, and welcome to today's Technical Strategy Explainer. Stepping into the role of your senior technical strategy consultant today, we are going to deeply deconstruct the massive, industry-altering shifts coming out of the 2026 SAE World Congress experience in Detroit. For those of us actually engineering the future of global mobility, I want to give you our McKinsey-style executive thesis right up front. The era of blind, singular electrification is officially over. What we're seeing now is a permanent paradigm shift toward a highly pragmatic systems engineering imperative. We are pivoting from a monolithic push for battery electric vehicles to a really diversified multi-pathway propulsion ecosystem. Okay, let's dive into the details. This quote right here from the SAE proceedings absolutely nails the massive pivot we're witnessing. For the professional automotive engineers tuning in, you already know that geopolitical realities, specifically the supply chain vulnerabilities surrounding critical battery minerals, have basically forced a total recalibration. We just aren't optimizing for end-of-pipe, tailpipe emissions anymore. The new engineering mandate is complete lifecycle sustainability. It's a fundamental structural realignment, and it's being driven equally by applied physics and global macroeconomic realities. So, to digest the hundreds of technical papers from WCX 2026, we're going to use a strict top-down MECE framework that's mutually exclusive, collectively exhaustive. Our agenda focuses on three core pillars. First, the operating environment and regulatory compliance. Second, we'll move upstream to LCA automation. And finally, we'll tackle the downstream circular battery economy. Let's jump straight into Pillar 1, the operating environment, and specifically how we navigate fragmented global regulatory compliance. The strategic takeaway answer first is this. As mobility engineers, you now have to navigate a totally fractured, hyper-regionalized policy map. You just can't design a single static global platform anymore. Winning in this decade demands highly modular hardware architectures that can adapt to wildly different regional constraints. For instance, in the US, the EPA has actually provided some crucial breathing room by delaying light-duty Tier 4 standards and relaxing CAFE expectations, acknowledging that these shouldn't be weaponized to force pure electrification. But then you look at California, and CARB is aggressively pushing Tier 5 draft standards for non-road engines, demanding ultra-low NOx through Tech Lake cylinder deactivation. Meanwhile, over in Europe, the EU introduced a 3-year average emission evaluation for 2025 to 2027 to give OEMs some flexibility, but their Euro 7 mandates are going to require really intense onboard monitoring. So you've got 3 regions requiring 3 completely different engineering responses.
Translating all that policy into actual hardware means we need highly specific emission control solutions. For Euro 7 and EPA 2027, engineers are heavily leaning into selective catalytic reduction on filter, or SCRF. This is absolutely crucial because it combines NOx reduction and particulate filtration into a single substrate, saving precious packaging volume. And for heavy-duty compliance, we're seeing the sheer necessity of AMOX, ammonia oxidation catalysts, to strictly control ammonia slip during transient operations. You know the drill. Every single millimeter of packaging space is literally a battleground right now.
Which brings us to one of the most mind-blowing highlights from the Congress, 43.1%. This number basically represents the thermodynamic renaissance of the internal combustion engine. Specifically, this is the brake thermal efficiency achieved by IAV's new 11.6-liter heavy-duty gasoline engine. Think about that. To bypass the incredibly complex and incredibly expensive diesel aftertreatment systems required for EPA 2027, engineers are radically reimagining the heavy-duty auto cycle to actually rival diesel efficiency. Let's geek out for a second on how they actually hit that 43.1%. The IAV 11.6-liter architecture uses a staggering 16-to-1 geometric compression ratio, and they pair that with extreme Miller cycle intake valve timing to prevent knock while maximizing the expansion ratio. It also utilizes stoichiometric EGR to keep a massive 40-liter single-unit 3-way catalyst fed and perfectly happy. So what's the so what here for Tier 1 suppliers? Well, if you want to achieve EPA 2027 compliance using this really economical gasoline architecture, your global vehicle platforms have to be modular enough to package a 40-liter catalyst. That is a massive packaging constraint that completely alters the entire chassis layout.
Moving upstream, we arrive at Pillar 2, upstream engineering, focusing heavily on life cycle assessment, or LCA, automation. We are witnessing a profound philosophical shift in the industry. Environmental impact evaluation has officially moved from the end-of-pipe, tailpipe phase straight into the embryonic CAD design phase. This shift is being heavily driven by digital product passports, or DPPs, an upcoming European mandate that demands absolute, undeniable transparency. OEMs are going to need comprehensive material traceability and full cradle-to-grave carbon footprint declarations. DPPs represent a forced evolution. Those old-school manual post-design LCA calculations, where you find out your component failed its carbon budget right before production, those are officially financially and legally obsolete.
But there is a really elegant solution. SAE Technical Paper 2026-370044 presented a massive breakthrough. Instead of the traditional approach, where you literally throw a design over the wall for post-analysis and inevitably face costly redesigns weeks later, engineers can now use an automated design sustainability evaluation framework. By utilizing Visual Basic for applications, you can link 3D CAD models directly with real-time costing and lifecycle assessment databases. You're optimizing for mass, structural integrity, cost, and carbon footprint all at the exact same time, in real time, right from your workstation. It's a real game changer. When you start comparing LCA metrics for different materials, everything from fossil-based plastics to renewables to mechanically recycled composites, the trade-offs between cradle-to-gate CO2, water usage, and energy consumption become incredibly complex. It's like a giant puzzle. And since lightweighting is still the primary enabler for EV range extension, using these automated LCA tools is really the only mathematical way to ensure your new composite materials actually hit strict ESG targets without accidentally causing massive upstream damage. Now, let's shift downstream to Pillar 3, downstream management and the circular battery economy. As the auto industry scales up to produce tens of millions of electric vehicles, managing the millions of tons of highly complex electrochemical waste is basically our absolute defining challenge of the late 2020s. And the debate over end-of-life management has really crystallized into 2 diverging paths. On one side, you have second life reuse, taking degraded EV batteries and repurposing them for stationary grid storage. Now, this extends physical life, but it strategically strands critical minerals like lithium and cobalt for decades. On the other side, you have closed-loop material recycling. This involves super advanced hydrometallurgical or pyrometallurgical extraction to pull out high-purity elemental metals to forge brand new cells. This is great because it reduces reliance on monopolized foreign supply chains, but man, it requires staggering initial capex. But let's say you decide to pursue that second life reuse path. You immediately run into a massive bottleneck. How do you quickly and accurately assess the health of a used battery? Well, researchers have hit a 95.33% accuracy rate for determining a retired battery's exact state of health. And get this, they can do it in just 12 minutes. No way, right? So how do they actually achieve this? Well, as detailed in SAE paper 2026-01-7007, researchers utilized a deep learning-based screening architecture. By training a CNN transformer neural network on a database of 750 commercial retired batteries, they completely bridged the gap between highly variable hardware degradation and pure software intelligence. This AI-driven diagnostic leap is exactly the kind of innovation that makes scaled, profitable second-life applications technically viable for the first time.
All right, this brings us to our 2030 strategic imperatives. Let's synthesize this top-down approach.
Synthesizing our MECE pillars, the overarching truth coming out of Detroit is clear. Future market dominance belongs to organizations that can master electrochemistry, advanced software intelligence, and circular business models simultaneously. You literally cannot isolate these disciplines anymore. We are fully entering the decade of integration. We're combining the strengths of electric propulsion, ultra-efficient combustion, and digital control. Resource-conscious design, like rare earth-free motors, and technological pluralism are merging right now to form a highly resilient, heavily optimized global mobility ecosystem.
So, I want to leave you with a direct challenge as you look at your own organizational strategy. Ask yourself, is your engineering roadmap proactive or is it fundamentally reactive? Are you treating global compliance and lifecycle assessments as core integrated design variables right at the CAD level, or are they still just post-production afterthoughts? The paradigm has permanently shifted. The engineers and firms that internalize this multi-pathway, lifecycle-centric approach today, those are the ones who will be defining the roads of 2030. Thank you so much for joining me for this explainer, and keep engineering the future.
Welcome to this explainer. I'm putting on my hat as a senior technical strategy consultant today to deliver a top-down, McKinsey-style briefing on the absolute bleeding edge of vehicle dynamics. We're pulling directly from the technical proceedings of the SAE WCX 2026 Congress. Look, if you're a professional vehicle engineer or a technical lead trying to navigate the massive shift towards software-defined vehicles, or SDVs, you are exactly who this is for. We're skipping the marketing hype and diving straight into the physical and algorithmic realities of the 2026 handling paradigm. To keep things sharp, we're strictly following a MECE framework today. Mutually exclusive, collectively exhaustive. We'll quickly hit the new handling paradigm, dive into DRL-based torque vectoring, unpack smart corners in wheel propulsion, look at active suspension kinematics, and wrap up with your strategic takeaways. Let's just jump right in. Section 1. The new handling paradigm, and how we actually overcome the SDV mass penalty. All right, so here's the reality check. The transition to heavy, electrified, software-defined vehicles has completely shattered our traditional chassis engineering rules. We're suddenly dealing with these massive, high-voltage battery packs that slap hundreds of kilograms of sprung mass onto the chassis. That radically alters both the overall mass and the yaw moment of inertia. Because of this, we literally have to throw out those legacy linear bicycle models we've relied on for decades. Instead, modern chassis control forces us into complex, multi-body state space representations. In these new mathematical models, parameters aren't just static constants anymore. They're time-varying variables dictating lateral response. Mastering this state space formulation, it's no longer optional, it's the absolute baseline for modern handling. Which brings us to Section 2, DRL-based torque vectoring, or the control logic layer. So to manage all these incredibly complex lateral and longitudinal dynamics we just talked about, we have to look at the evolution of torque vectoring. Now, pay attention to the shift in computational strategy here. Historically, we engineers leaned hard on nonlinear model predictive control, NMPC. Great fidelity, sure, but it requires massive, power-hungry processing to constantly calculate future constraints. Well, the WCX 2026 proceedings highlight a massive pivot away from that, moving straight toward actor-critic deep reinforcement learning, or DRL. Why? Because it delivers that same high-fidelity handling for highly nonlinear tire models, but with radically lower computational requirements at the edge. It is, frankly, a total game-changer for onboard real-time processing.
Comparing these dominant control methodologies side by side really tells the story. Sliding mode control, SMC, is still super robust for basic stability, right? And MPC is great for high-precision path tracking. But DRL? DRL is the absolute emerging champion for torque vectoring. Because it's trained offline on high-fidelity multi-body simulations, these DRL-based controllers completely outperform conventional methods across rapidly changing road frictions. Imagine hitting a sudden patch of black ice. DRL handles it smoothly, without maxing out the vehicle's processing overhead. It's incredibly efficient.
Okay, so how does this actually look in the vehicle? It relies on a multi-layer framework. First up, you have an adaptive high-level controller, typically an ALQR, which shapes the desired yaw response based on what the driver is doing. Then, right beneath that, a low-level allocation layer uses quadratic programming to solve the exact torque distribution across the individual motors, and it does this in mere milliseconds. But here is the really surprising takeaway. This setup doesn't just give you extreme agility. By managing tire slip this precisely, it actually yields up to a 10% energy savings in specific drive cycles. You are literally converting better handling into longer electrical range. How cool is that?
Moving on to Section 3, Smart Corners in-wheel propulsion, focusing on hardware integration.
All right, translating all this software into physical packaging ushers in the era of the smart e-corner. This is a highly modular system that consolidates propulsion via in-wheel motors, steer-by-wire functionality, seamless brake blending, and active suspension, all tucked entirely within the wheel envelope. Think about what that means. By pushing all that dynamic hardware to the four corners, you completely liberate the central floor pan. No central traction motor, no differential, no half shafts. This unlocks true skateboard chassis modularity. An OEM can essentially scale from a compact city car right up to a commercial van on the exact same base platform.
Now, I know what you're thinking. Any seasoned chassis engineer watching this immediately zeroes in on the elephant in the room, the unsprung mass penalty. For years, the industry vehemently rejected in-wheel motors because slapping all that mass directly onto the hub destroys ride quality and messes with tire contact patch consistency. But here is where it gets fascinating. The Smart Corners initiative actually negates this physical limitation through advanced software. By coordinating ultra-fast active suspension actuators via high-speed deterministic AI networks, the system proactively manages those wheel dynamics in real time. It effectively masks the physical weight penalty, proving that, yes, algorithmic control can indeed overcome legacy hardware limitations. And that leads us perfectly into Section 4, Active Suspension Kinematics, or Mastering Vertical Dynamics. Keeping heavy SDV sensor platforms perfectly stable requires managing some severe vertical dynamics, and that takes a brilliant division of labor. Traditional suspensions always force a compromise between comfort and handling. But the WCX 2026 solution, it's a hybrid suspension architecture. It uses continuous hydraulic dampers to handle the heavy lifting, high-force, low-frequency movements, like resisting body roll in a tight corner. But simultaneously, you have these hyper-fast electromechanical actuators punching out high-frequency, low-amplitude disturbances. Think bridge expansion joints or a nasty stretch of cobblestones.
But to actually govern this sophisticated hardware, classical skyhook theory is getting a massive upgrade. Engineers are now implementing fuzzy neural network PID controls, or FNN PID, to instantly process huge data streams from inertial measurement units and wheel speed sensors. This algorithm dynamically tweaks those hybrid actuators in milliseconds. The goal here is basically the perfect mathematical ideal, completely isolating the sprung mass from chaotic road inputs. It's almost like the chassis is floating.
Finally, Section 5, Strategic Engineering Takeaways, where we synthesize this entire 2026 paradigm.
When we synthesize all these domains, one massive overarching theme emerges: systemic integration. The days of engineering subsystems in silos are completely over. Your DRL software, your smart corner hardware, and your active suspension kinematics absolutely must be strictly co-developed. To succeed in this era, you have to master extreme platform modularity. And all of this has to be linked by a unified digital backbone, which means relying heavily on zone-based EE architectures and centralized compute platforms to drastically kill latency.
So I want to leave you with a critical question regarding your organization's technological sovereignty. Is your OEM or your Tier 1 supplier's centralized compute architecture truly prepared to govern the incredibly complex real-time interplay of AI algorithms, smart in-wheel hardware, and active kinematics that will totally define the market by 2026? Because honestly, if you're still engineering isolated components rather than optimizing whole ecosystems, you are already falling behind. Thanks for tuning into this explainer, and I'll catch you next time. All right, let's get right into it. For all you automotive engineers and architects watching this explainer, we are deconstructing the single most critical engineering shift coming out of the 2026 SAE WCX, the software-defined vehicle, or SDV paradigm. Look, we have to establish the macro-level crisis right up front. The traditional engineering model, the one relying purely on mechanical optimization and those legacy distributed electronic architectures, it's officially hit a physical and logistical wall. Stacking well over 100 isolated electronic control units into a single vehicle has created a total complexity crisis. The wiring harnesses are way too heavy, the assembly is a manufacturing nightmare, and the computational inefficiency is just staggering at this point. To survive, we absolutely have to rethink the entire vehicle as a high-performance computing platform.
Okay, so here is our strategic blueprint for the SDV ecosystem. We're taking a rigorous top-down approach today, broken into 3 core pillars. First, vehicle software and hardware. Second, zonal and centralized EE architectures. And third, OTA updates and monetization.
Let's kick things off with pillar number 1, vehicle software and hardware. This is the absolute base layer of the entire SDV ecosystem. Let's state the conclusion first. True software-defined vehicles demand an uncompromising, complete decoupling of software from physical silicon. And how do we actually achieve that? Through virtualization and hypervisors. Think of a hypervisor, which is managed by a virtual machine monitor, as the ultimate traffic cop for your processing power. It neatly partitions the resources of a single, highly powerful compute cluster. This is a game changer because it lets us run mixed integrity workloads right next to each other perfectly safely. So you can literally have a hypercritical AUTOSAR-based safety application running securely right alongside a standard Linux infotainment system. If the infotainment crashes, no problem. The hypervisor guarantees absolute freedom from interference. Your vehicle's braking and steering remain perfectly safe and 100% compliant with ISO 2626 functional safety standards. Now, what's really fascinating here is the software factory approach. Because we've successfully decoupled the software using hardware abstraction layers, we completely unlock parallel engineering cycles. Software engineers no longer have to sit around waiting for physical silicon prototypes to be manufactured. Instead, they use virtual development kits and cloud-native simulation environments to design, test, and validate millions of lines of code. And they do this months, sometimes even years before the hardware actually exists. This massive shift left in the development timeline is absolutely crucial. It's what drastically reduces our time to market for these incredibly complex service-oriented architectures. Moving right along to our second pillar, zonal and centralized EE architectures. This acts as the structural layer of the SDV ecosystem. Looking at the WCX data, this structural shift isn't just a nice-to-have, it's a hard manufacturing imperative. We are finally moving away from those old functional silos, where you've got one ECU for the windows, a totally different one for the wipers, and another for the seats. It's just not sustainable. Instead, we're grouping components purely by their physical location in the car. Think front left zone or rear right zone. By doing this, we're consolidating well over 100 isolated legacy ECUs down to fewer than 10 high-performance compute clusters. And this brilliantly illustrates the stark contrast we're talking about. On the legacy side, you've got this absolute rat's nest of point-to-point connections. It creates exorbitant wiring harness weight, which is literally dragging down electric vehicle range. But on the zonal side, we have simplified high-speed data backbones. We are shedding all that massive physical weight and replacing highly limited CAN buses with deterministic multi-gigabit Ethernet. In this setup, the zone controllers basically act as data aggregators. They just scoop up massive streams of sensor information and fire it straight up to the central high-performance computer. And hey, if you need financial proof, this technical transition is completely undeniable. From a strategic investment standpoint, the zonal architecture market is projected to absolutely surge to $24 billion by the year 2036. That is a massive 16.1% compound annual growth rate. Even looking closer, by 2026 alone, it's expected to command a 55% share of the architecture market. So to put that bluntly, engineering teams that are still designing around distributed domain controllers, you are building for the past. Okay, so once we've successfully decoupled the software and centralized the hardware, how do we actually generate continuous lifecycle value? That brings us to pillar 3, over-the-air updates and monetization, the true value layer of the SDV. But listen, before we can even start dreaming about seamless OTA updates for consumers, we have to solve a massive, glaring manufacturing crisis. How do we bypass the huge bottleneck of end-of-line ECU flashing? Traditional end-of-line flashing, where a finished vehicle is hooked up via an OBD2 port at the very end of the assembly line, has just completely collapsed. It's buckling under the sheer volume of these gigabyte-heavy SDV software packages. The limited bandwidth of those old diagnostic tools is severely dragging down factory throughput. I mean, you absolutely cannot have a highly optimized mechanical assembly line grinding to a complete halt just because you're waiting for software to download. It makes zero sense.
So what's the fix? The engineer's solution presented at SAE WCX is Vehicle Lifecycle Management, or VLCM. This is a total paradigm shift. We are taking software configuration and transforming it from an isolated assembly line step into a continuous, end-to-end secure distribution process. We're talking about deploying offline, parallel, and just-in-time flashing ecosystems. Software is now loaded onto components right at the Tier 1 supplier level. It's updated in parallel during subassembly, and it's seamlessly managed out in the factory yard. The vehicle is quite literally born digital, and it stays connected to a central database from the factory floor all the way to the customer's driveway.
Yet despite all this brilliant engineering, here is the harsh reality for the value layer. Right now, an alarming 94% of Western automakers fail to monetize more than half of their deployed SDV capabilities. 94%. Why is that happening? Well, it's because they're still treating software like a static mechanical feature. They're trying to force basic, frankly annoying subscriptions onto consumers for legacy functions. Look, consumers spending $80,000 on a vehicle expect automatic, meaningful feature enhancements. They don't want bug fixes masquerading as updates, and they definitely don't want paywalls just to turn on their heated seats.
To survive and actually overcome this massive monetization gap, OEMs have to fundamentally shift their mindset. We must stop treating vehicles as static mechanical products. We need to elevate the vehicle from merely being software-enabled to becoming a Level 5 innovation platform. What does that mean? It means the vehicle operates just like a smartphone ecosystem. The hardware's true potential is unlocked over time. Just imagine this. You sell a customer a comfortable, everyday commuter car. Then, via a secure weekend OTA update, their unified domain controllers dynamically retune the suspension damping and torque vectoring, completely transforming it into an aggressive track car. Now that is true lifecycle value.
So I'm going to leave you with this provocative engineering challenge to wrap up this explainer. To truly master this great decoupling, you have to ask yourself, is your organization actually structured to engineer a 2,500 kilogram vehicle as a continuously evolving Level 5 innovation platform? Are you honestly prepared to prioritize software architecture, virtual validation, and agile continuous integration over traditional mechanical optimization? Because the paradigm has officially shifted. The hardware is just the host now. The software is the vehicle. Think hard on that as you design your strategic roadmaps for 2026 and beyond.